be working. Good afternoon, everyone. I think I'll just go ahead and start here. Thank you all for joining. Thank you for the organizers for giving me the opportunity to talk about some of the stuff I care about here. So the title of my talk is Bringing Digital Signatures and Pki to the Masses with Python. So the thing I want to discuss today is how we can enable more, let's say, quote unquote, ordinary people to use serious digital signature tooling in their, well, everyday workflows in their daily lives. Right, so one quick slide about myself. I am a former research mathematician, now working as a software developer. I like cryptography and digital signatures, otherwise I wouldn't be here giving this talk. But my day job is actually in the digital documents industry, so I work mainly with PDF files in my day job. It's kind of related, but you know, there's obviously overlap, right? But, yeah, I'm not going to talk about PDF today. So I am also a very active contributor to various open source projects. So I've listed two that I set myself here. I'll talk about these at the end, just to give you an idea, because they are relevant for the talk, obviously. Otherwise, I wouldn't, make any mention of them. And yeah, the usual disclaimer: any opinions expressed in this talk are my own, just so you know. And for those that would prefer mobile slides, I put a QR code here. I took the example from the previous talk, and it was a good idea. So if you want to scan it now, it's time. Moving on, okay. So I'll spend quite some time talking about what Pki is, because I imagine that not all of you in the audience today are familiar with what all of that entails. So yeah, let's set some things up. So Pki is an abbreviation. It stands for Public Key Infrastructure. That in itself doesn't say very much, but you can think of it as the thing that makes certificates work, basically. So it's the infrastructure, and everything that goes into that makes certificates in all their use cases basically tick. That's sort of the idea. So among other things, HTTPS is powered by Pki. Code signing in Windows and other platforms is powered by Pki. Digital document signing is powered by Pki. All sorts of things that you're probably using every day without necessarily realizing what all of that is about. But yeah, for today I'll talk about Pki as used in the digital signing context mostly. So I won't be discussing encrypting data. That's all out of scope. I mean, it's relevant, but it's not the main point I want to make. Right. So the logistics of a digital signature. How does that actually work? So the requirements are usually, well, there's obviously some variation in the requirements, but the basic ones are kind of usually always the same. And as is tradition, my two interacting parties will be called Alice and Bob, right? Because everyone does that, so of course I should follow suit. And the scenario is that Bob wants to send a message to Alice, and Alice wants to make sure that certain properties are satisfied. So she wants to make sure that the message was not tampered with in transit. That's an integrity requirement. Then she wants to make sure that the message actually came from Bob and not someone pretending to be Bob, right? That's an authenticity requirement. And then usually, she also wants to be able to hold Bob to his word. So that's a fuzzy one. Actually, what that boils down to is being able to prove to a third party, say for example, a judge, that Bob actually sent that message. And there is a very interesting world of deniable signatures that don't have this property, but usually in scenarios we care about in real life, this is something you want. Right, so we've talked about the requirements, and let's talk about the basic process. Of course, Bob starts by writing his message in whatever format he prefers. Then he signs the message using his private key, using some signature algorithm, whatever that is. And then Bob sends the message plus the signature to Alice. Then on the receiving end, Alice verifies the signature using Bob's public key. So the public key is intended for verification, and the private key is intended for actually performing the signing operation. So that's the key principle here. There's a private key, there is a public key. The private key is obviously private, so only Bob knows the private key, and the public key is available to anyone that wants to verify the signature. That's the idea. But is it really that simple? Probably not, right? Otherwise I wouldn't be asking the question. So there are a bunch of second order problems here. So indeed, Alice can now verify whether the that she received or that she's using matches the signature. That's straightforward. That's just maths. She can also verify that the data wasn't altered after signing. That's also cool. But there are various things that are much more subtle here. So how does Alice obtain a copy of Bob's key in the first place? So she has to get access to that key in some way, right? So perhaps it's a file server, perhaps Bob sent it to her some other time, perhaps they met up in a parking lot somewhere and exchanged keys, that's also possible. How does she know that the key is really Bob's, right? Because not all of these methods are obviously secure, right? So if Bob meets Alice in the parking lot, sure, then she can look at his face and visually confirm that it's actually Bob. Whereas if she just downloads the key from some file servers, who knows? And then the third property, which I won't talk about that much today, is again this accountability thing. So no single step in this process ensures that Alice can also prove the validity of that message to other parties, right? That's something that's also not guaranteed here. But yeah, you can forget about that last one. I put it in here for completeness, but it's not the most important thing. But it's this kind of problem that Pki is designed to address. So that's sort of, it's one of the frameworks in which you can deal with this sort of problems. So let's talk about maybe the key distribution problem first, because that's the easiest one to at least conceptually understand. So how does Alice get a copy of Bob's key? There are at least 3 methods that I put here on the slide. So one is pre-sharing the key using some out-of-band mechanism. Again, parking lot is one such mechanism. But obviously that doesn't scale, right? You couldn't just arrange meetings with everyone that you want to exchange keys with, and just not practical in real life. Then there is a web of trust way of doing things. The basic idea here is that you have a bunch of users that sign other people's keys. Basically, you get someone to vouch for you, and if then the person that you want to send a message to already trusts that other person, or perhaps several people, then they trust your key. If not, then they don't. The problem there is that it does scale if implemented properly, but it requires disciplined users, and who has those, right? Nobody does. So that also doesn't really work. It does, but only in very limited circumstances. Then the third option is what is used the most in practice. That's relying on a certificate authority. So basically, there's some third party that everyone trusts for whatever reason. And basically, that third party has the job of assigning keys to people. So they basically certify that a certain public key belongs to a certain entity, whether that's a person or a company or a government, doesn't matter. Just their only job is linking identities to keys. It's not their only job, but it's kind of the gist of it. So, of course, the issue there is that you end up with some degree of centralization in your trust system. There are ways to mitigate that, which I won't go into, but there is some sort of trust requirement with you need a trusted third party. And it has potentially many single points of failure. So if you have multiple CAs that everyone trusts, then only one of them needs to be compromised before everything is proved. This sort of centralization tends to make sense in a lot of scenarios, right? Decentralized signatures is not something that is commonly needed. So in practice, this is something that people converge to in reality. So there are many certain scenarios where it's obvious that this makes sense. For example, say government PKI, like national ID. Like many countries in Europe have ID cards now with keys on them. This is mine. So there are multiple certificates actually on this card. They are guaranteed by a government CA. And that makes sense, right? Because the government is a central entity. And when doing government business, everyone should hopefully trust that the government makes correct statements about who people are. Another scenario is, for example, enterprise PKI, where you have like a huge company that needs to do dealings between departments. At some scale, it starts to make sense that they just maintain their own PKI instead of outsourcing that. Yeah, sure, that's also an obvious case where there is a central authority available, why not use it? And then, the other thing is for certain public workflows, and that's a scenario that is perhaps the most common in practice, where there is there is a group of companies, say, that people generally trust. and those are, well, commercial CAs then, and they issue certificates to companies for money, or to people for money. Yeah, that's a very unfair summary of the state of affairs, but you'll have to make do with that. Great. So how do the actual certificates work then? So a certificate is kind of just another signed piece of data, and it binds, as I said before, a particular public key to its owner. So the entity that issued the certificate is called the certificate authority. That's kind of the idea here. So it's just a signed statement by the CA, plus metadata, right? So there is the subject name and public key. That's obvious that you need that. Then there is the issuer name, the validity period, info where to retrieve, all sorts of validation status information, blah, blah, blah. A bunch of other things, but the essence is that it binds a key to its owner. That's, if you remember that, that's okay. And of course, you can have multiple layers of that, right? So in practice, trusting all sorts of certificate authorities directly is also not practical for various reasons. So, well, CAs delegate to various sub-CAs, and you end up with a chain of CAs, and it's CAs all the way down, but at the end, you have to end up at some trust anchor that is pre-installed in your machine, for example. So let's go back to our example. How does that work in practice now that we have certificates? So when Bob sends a signed message to Alice, what he does is he attaches a copy of his certificate to the message. And what Alice can then do is verify that the name on the certificate, well, it matches what you think it should be, namely Bob's name. And then also she verifies the chain of trust. And if everything checks out, so if everything chains up to a CA that Alice already trusts, then she can use the public key in Bob's certificate to verify the signature. That's again the basic idea. Of course, in practice it's more complicated than that, but this is good enough for the first approximation. But yeah, real life is hard. So in real life, you also have to deal with revocation, interaction between multiple signatures. That's very file format specific. Who knows, right? There's timestamping, archival requirements. Enforcing all this accountability business is also not trivial in practice. Again, concerns specific to file formats, right? Because signing a PDF is not the same as signing a docx file or an XML document. Every format has basically their own way of doing things. It kind of depends, right? Can talk about that for hours. Catch me in the hallway after. Somehow all of this complexity has to be transparent and auditable and user-friendly all at the same time. And you can imagine that that's pretty difficult. So, right. How about Pki in daily life? What do we have going on there? So Pki as a technology or a set of technologies is by no means new. It's been around for decades. And even pretty complicated Pki has been used in governments and large enterprises for tens of years. There's really nothing new there. Also, HTTPS has been using Pki for a long time, and cryptographic document signing in particular also is not really new. So why am I talking about this now? Well, the past couple of years, well, obviously more and more people have been having to deal with digital workflows of various natures. And certain things seem to have changed in the landscape in the meantime. So, well, there are more paper workflows that are now conducted in a digital manner. Even many small businesses that usually would rely on paper stuff and not have to deal with digital signing are now forced to adapt, right? Or have been forced to adapt. And big business takes advantage of this, right? So there are various proprietary signing platforms and tools that have been gaining popularity. There's a lot of buzz in that market, which in itself is not a bad thing. But it's kind of unfortunate that the open source world seems to be lagging behind a bit. And that's the topic that I want to get into today. So, why is this a concern? Well, there are certain business practices, and I want to explicitly refrain from making any concrete accusations here, never know, that kind of end up depriving individual users of agency. So some examples here. I've had all of these happen to me at some time. So sometimes you get invited to sign like a contract on some sort of walled garden online platform that's managed by some private company, and the person that you're dealing with just emails you a link and they tell you click there and it'll make it work. Right, but as a user you have absolutely zero control over what happens next. Right, it's very unclear how all of these authenticity mechanisms work. It's unclear how these are enforced or enforceable after the fact, right? If that company goes out of business, what happens next? I mean, all sorts of funny questions. So that's one thing that happens. The other thing that happens is when you deal with certain private companies that need to work with or collaborate with government PKI, even in countries where the government has a pretty significant open source presence, which is the case in Belgium, where I'm from, you often still have to install some kind of binary blob that talks to your ID card and makes the application work. Obviously, that's also not very nice, because now I have to kind of entrust the secret data on my card to some, well, application that I can't inspect, which I also don't like to have to do. In a similar vein, well, cross-platform support for these blobs is non-existent in practice. So they usually do Windows and usually only one browser. And if you're very lucky, they might have a Mac build. But Linux, good luck, right? It's not happening. And then also, yeah, they kind of alluded to this before, but there are no standard tools to guarantee the longevity of these delegated signatures. So if you have a company sign on your behalf, well, it's very unclear how you would be able to, let's say, preserve the intent of the signer in such a format over time. So at best, well, there are mechanisms in PKI that allow you to preserve the validity of signatures with particular keys and certificates. That all makes sense. But since here, the entity that's actually doing the signing is just some company with a certificate of their own, it's very difficult to somehow gauge how they distinguish between users and how they preserve that information over time. You can't know that. There's just no way that can work in general. So these are all pretty vague concerns, and I'm certainly not in the business of proposing solutions for all of these things. I won't claim that we can do that just that easily. But I do believe that there are a number of things that we can do as a community to improve the general situation and give more people access to, well, tools that they can make use of in their own lives, both as users and as developers. Right. So some proportion, again, not all of them, not all of these issues can be addressed, but some of them can be addressed by building better open source software for these relying parties. So what I mean by a relying party is not a company that actually manages PKI, but a company that interacts with PKI or interfaces with PKI to do things. And yeah, that obviously covers a very wide range of use cases, right? So basically any case where you are in the business of signing, let's say, invoices that you send to people, well, that's one example of a situation where you would be acting as the relying party. So a number of obvious examples here. So document signing on the Linux desktop, the state of that is pretty poor, unfortunately. So there is very rudimentary support in Ocular and LibreOffice Writer. I mean, good job, right? Really, I mean it, but it's just not there yet. Yeah. So mostly on the validation end, there is too much. Well, there are too many asterisks. Let me put it that way. Again, catch me in the hallway if you want to hear me rant about this for even longer. But in general, we also need to make more effort to work towards explainable PKI. So again, PKI is complicated stuff, and explaining that to people is hard. I'm trying today, but who knows if I'm succeeding. And it's in particular very hard to explain to a user what it means when they put in a digital signature. What are they actually committing to? And again, there are standards describing all of this stuff. I mean, the technical story is very, well, not very, but kind of, at least there is a framework. And there is the technical framework by which we can make all of this work. However, even if all the technical problems are solved, we don't really have a way to make that accessible to, even power users, right? Because if you grab someone off the street, even at a technical conference, it's not really a guarantee that they will understand all of the subtleties in workflow like this. And I believe that making Pki more accessible includes making it more explainable, so making it more clear to individual users what they are actually doing when they sign stuff. So yeah, that includes certain cryptographic concerns. So you can't translate any real-world requirement into a cryptographic equation. That's just not possible. But well, in the cases where you can, it should be clear what is covered and what not. Also, which parties guarantee what, right? Like a timestamper, for example, usually will not make any commitment to the content of a document. They basically just say, okay, I saw this hash at this point in time, period. They're not saying anything about the veracity of whatever's in the message, right? Whereas a human signer might be expected to actually live up to something that they put in that message. So which parties guarantee what is a very broad but very important question that needs to be absolutely crystal clear to all the parties involved in any given digital signing workflow. And I've already mentioned validation, right? Validation is very complicated. It has lots of knobs and parameters and policy requirements and whatnot. Yeah, it's very hard to get right. So where can Python step in? So software relying on Pki isn't magic. And actually, the mathematics is pretty much the easy part. So we have libraries and hardware to do that for you. So I already showed the ID card. This is another example of a device that can produce signatures. I mean, yeah, the difficult, secure mathematics, that we have stuff that can do that. Now, all the stuff in between, so all the policy requirements, enforcement, talking network services, file format-specific concerns like signing PDFs, signing XML files, whatever. All of these things, well, we need glue code to handle that. And we need good glue code to handle that because none of this is trivial. I mean, it kind of sounds like, well, cryptography is all about doing crazy math, but yeah, sometimes the glue code is more important. And yeah, I think that's exactly where we as a community have a job to do first. So yeah, Python is a pretty good fit for this sort of high-level application logic. Interpreter languages are also very good for transparency, right? Because you can just go and read the source that's running on your machine. Very nice. And just in general, the Python community has a pretty good track record of maintaining nice user-friendly tools. My opinion, but I think it's true. So I've been doing some work in that space myself. Here are 3 projects that I've worked on in the past 2 years and change. So I have my own PDF signing library that's sitting out there on GitHub. So it's both intended as a CLI tool for power users to do signing on the desktop, but also to act as a library for signing files. It's kind of intended as a Swiss Army knife. So yeah, it is capable of doing a lot of things, but not necessarily doing them in the most user-friendly way. So again, I'm not in the business of providing nice UIs and stuff. I hope someone else would eventually take care of that. Then I also have a certificate validation library that's basically a fork of someone else's, but I added a bunch of stuff. And then I also have a testing framework for Pki stuff. And I like to focus on that one for just 30 seconds, because testing this stuff can be pretty complicated in practice, right? Because setting up an actual test environment takes a lot of work. And having something that you can use to quickly spin up test configurations that have all these fancy trust services like OCSP, CRLs, timestamping agents, blah, blah. Having that just in a couple lines of YAML configuration is pretty useful. Speaking for myself here, but they use this in the test suite for the other 2 tools, so it works for me. Right, so quick conclusion. The demand for Pki and digital signing is still growing. Governments and industry continue to invest in this space, but the tools for power users are often still lacking, if I say so myself. And there is a gap for FOSS and Python to fill there. So take this as a call to action to contribute to this space if you have the time and will to do so. Thank you.